I'd like to do one concrete calculation of a forced oscillator, meaning really starting from the basic equations and deriving the amplitude equations, and then actually also analyze them, which would be more of a computation. And I want to do that for the 3-to-1 forcing, which is an interesting case, as you'll see. So let's first derive the equation, the form of the equation, and then we know the scaling and so on and so on. So for 3-to-1 forcing, we think that we have an oscillator Y, and it would have an amplitude e to the I omega naught t, and the higher order terms. And the forcing is now at 3 times that frequency. And so we would have e to the 3 I omega naught t. And so when you then look at the selection rules, which I'm not going to go through in detail, it's the same approach as we've done before, and it's written out in the notes. And so if you look at the leading orders in F, there's a term that could be an F. Well, the selection rule requires if there's an F, it has to be an A star squared. And you could also have a term F star, but it would require a term A to the 4th. And so if you look at the leading order terms, then obviously this is higher order than that. And so we focus on this term. Then, as before, we want to have also saturation of the amplitude. So we want to have that is FA star squared, so of the same order as A absolute value squared A. And therefore, F should be also the order of A. And then you, after a little bit more considerations, you find out that the equation that you get has the following form. dTA is equal to your control parameter plus a coefficient F absolute value squared times A minus gamma absolute value squared A plus delta F A star squared. I've chosen the sign of the coefficient here such that I'm assuming gamma is positive and I want to have the saturating. That's just my choice. It's not profound. Okay, so we see that the F shows up in 2 different ways. First, it shows up in terms of the absolute value squared. And here it modifies the coefficient mu. So that means the real part of beta modifies the growth rate of A. Well, I shouldn't say the real part of beta tells us how the forcing changes the growth rate. An imaginary part of beta tells us how the forcing changes the frequency of the oscillation. This is actually the same kind of term we also had in a non-resonant case. So this is a very generic term, and it will pop up everywhere. The qualitatively new, and it doesn't lead to any qualitative changes. It just means that the onset is shifted and the frequency is shifted, but the solutions look the same. The qualitative new solutions come again from this term, which is a new term, and it is phase dependent, as in it breaks that symmetry. Like without forcing, we have this phase shift symmetry, and that is broken by this term with delta, by this delta term. And therefore, it leads really to qualitatively new phenomena, and is the most interesting part. So that is the equation which you expect for essentially any oscillator if it's forced at 3 times its natural frequency, except what can happen is that there's additional symmetries in the original equations. For instance, if it just so happened that the original equations had a symmetry y going to minus y, which would mean the final equations would have to have a symmetry a going to minus a. In that case, this term would not be allowed, right? So the equation would change significantly in such a case. But the important point to make here is that the only thing that can happen with additional symmetries is that coefficients are 0. The time translation symmetry that we used already rules out or set a whole bunch of coefficients to be 0, and they cannot become non-zero because of some other symmetries. You only can have additional coefficients dropping out if there's additional symmetries. Okay. So of course, okay, I mentioned that before, I think also that in principle, symmetries, of course, allow also, like, say there's a term here that would modify gamma with f absolute value squared. So in principle, that one could add here, one would expect here a term like gamma 2 f absolute value squared in addition to the gamma. Formally, that is of higher order, and therefore we don't keep it, but it's also not of much interest, because as long as gamma is order 1, adding a small forcing term to it modifies the coefficient gamma, but that doesn't change the solutions in any qualitative form. It just means that the amplitude is slightly larger or slightly smaller. It only is relevant if gamma happened to be small, meaning if we were in the weakly subcritical or weakly supercritical regime, when the bifurcation is almost vertical. If gamma was very small or even 0, then of course this term would determine the sign of the cubic coefficient. And that of course makes a big difference. But in the generic case where these nonlinear coefficients are order 1, you can ignore safely the corrections that are arising from these additional forcing terms. With this analysis, you can also show, I'm not going to do that, but it's good to notice, or note, I should say, that if you had a higher resonance, as in you have forcing 4-to-1 or 5-to-1, you also get additional terms, phase-sensitive terms of that type. But you'll find they're all beyond cubic order. So that means if you only look at terms up to cubic order, which is sort of what you usually would do because that's where you get saturation, those terms would not show up. But they do make a difference. So, but they're sort of then weak resonance. They're not, in those cases, you don't have a strong resonance, just weak resonance. You change the solutions, but in a more subtle way. So therefore, the strong resonances are really when you force with 1-to-1, 2-to-1, or 3-to-1. Those are the strong resonances. Okay, so let's now embark on deriving the equation for a concrete oscillator. And let me pick the following oscillator. It's a d2y by dt squared plus beta dy by dt, some damping, plus omega naught squared y plus alpha y squared equals f of t. And I'm going to pick that, as I said, we want to do a 3-to-1 forcing. So we have, this is some amplitude f cosine 3 times omega naught. Well, we could make allow for a small change in the frequency. So there could be also plus, we don't know the scaling yet. So it's not clear how we should write that down. So let me maybe just dot dot, and we'll get there later. But we have here an explicit forcing term here. So let's first look at this problem and also see what we expect, right? So, oh, this is unfortunately far away. The equation we expect, based on our symmetry arguments, show that there's a nonlinearity that's cubic and one that is, well, quadratic in amplitude, but cubic in, but overall cubic. And F only shows up in combination with A, as in it's a multiplicative factor. That's true for this term and for this term. When you look at the equation that we're starting with, we only have a quadratic nonlinearity, no cubic nonlinearity, although we're going to get a cubic nonlinearity. And the forcing is actually an inhomogeneous term. I never defined that. So when forcing, one discriminates or distinguishes between two types. One talks about a parametric forcing. That's when a coefficient is time dependent. So, for instance, in a swing, that would be when you pump, meaning you're going to knees, you come up and down, which effectively changes the length of the pendulum of the swing, and that's a parameter in the problem. Whereas the non-parametric forcing is an inhomogeneous term. You have an inhomogeneous term. That's sort of when somebody stands behind the person and pushes the person on the swing. It's an additional, an external force. And if we look at it, in this problem, we have non-parametric forcing because it's really an additional force, whereas the parametric forcing would be if we had, say, picked omega naught to be time dependent, which is in the pendulum case. If you change the length of the pendulum, you change the frequency. So it would amount to having a time-dependent frequency here. But this forcing is non-parametric. However, the equation we're expecting to get has parametric forcing because F multiplies A star squared, and A. So I want to point that out because it's one of these examples where you can't really, just by looking at the original equation, say without further investigation what the final equation will be, what the form of it will be, because you can't just say, well, this equation is inhomogeneous, so the final amplitude equation is also an inhomogeneous equation. Or this nonlinearity, this is a quadratic nonlinearity, so therefore the final amplitude equation will also be quadratic. No, it's not true. That's not how it works. And so that's, I find that a very important aspect, so I wanted to, emphasize it. Okay, so now we're ready to roll. We need to scale stuff. So we see here, I guess we can write it down here. We see that from the general form, we see F is of the order of A, and mu is of the order of A squared. And so if we call A of order epsilon, then we have F order epsilon and mu order epsilon squared. And therefore also this low time order epsilon squared. So we introduce now for our expansion, we say y is equal to, as I said, order epsilon times y1, epsilon squared, y2, and so on. We introduce this low time epsilon squared t, and turns out that damping is also, we need to pick that order epsilon squared, so it also shows up in this equation, in the final equation. And the forcing F is I pick to be epsilon curly F. And therefore we also know how we should pick the frequency. We have the frequency omega is 3 times omega naught plus epsilon squared, capital omega. Okay, and we expect the solvability condition to kick in at order epsilon cubed. And that's that. So it turns out this calculation is a little bit lengthy. So I'm not going to go through all the steps. I just want to emphasize the key elements. Right? So you can look at the details in the notes, and even there you don't have everything because some algebra is just kind of like too much. So that's another case. You use mathematical maple, and then it's fine, but you don't want to. It's not much fun. Okay, so we'll go to order epsilon. Where do we go to order epsilon? Let's first look at it. Y is order epsilon, so we have a term from here. This is order epsilon cubed because beta is order epsilon squared. This is order epsilon. This is order epsilon squared. This is also order epsilon. That's a little bit surprising, so to speak, because you might have thought, well, based on all the previous examples that we did, it was always like, well, you have this linear operator, the linearization around the origin, and that's what you get at leading order. Well, in this case, you don't. You get this linear operator, yes, but there also the forcing is there already. So we have the equation at this order. It's given by d by dt squared plus omega naught squared y1, and that's equal to some inhomogeneous term, which is that forcing term, f. It's this guy, so it's a, what do we write down? The cosine, so it's 1/2 e to the I 3 omega naught plus epsilon squared capital omega. So that actually, maybe we should be explicit about it. We have that this f here is a function of slow time through, because we have here the omega term, capital omega term, with order epsilon squared. So let's maybe write it out. We have here, this is 1/2 f. So let me see, do I want to call this f? Let me call this, I'll put a hat on here, and the f is really the amplitude of this thing, and it's e to the 3I capital omega capital T times e to the 3I omega naught fast time plus cc. So that's this inhomogeneous term. Okay. So then we need to solve this. This operator here is linear, singular. And of course, its singular modes are e to the I omega naught t plus and minus. We also have here e to the 3I omega naught t. But with respect to that time dependence, L is invertible. So it's not, that's not an issue. So we can solve for it. So at leading order, let me just write it down what we get. We get like a times e to the 3I omega naught t. No, not 3, sorry. Not t. Not e to the I omega naught t. And a is still undetermined. That's the usual situation. That's our Hopf mode. And then we get a b e to the 3I omega naught t plus cc. And as I said, a is undetermined, but b can be calculated. It's determined. Let me just write it down what it is minus 1/16 omega naught squared f times e to the 3I omega t. Okay, so we have now y1 to the extent that it's determined at order epsilon. Order epsilon squared, what happens? Order epsilon squared, let's go and look. Epsilon squared, of course, we get the linear operator acting on y2. This term is not there yet, but we get something here from y squared, which is a y1 squared. So we have to look at what happens when we square y1. We have nothing on the right-hand side because f is really only order epsilon. There's no additional terms. We only have to look at y squared. And what does y squared do? Well, in this case, that's why the algebra becomes sort of unpleasant. You have to square this object. And so you get, of course, as always, 2 omega naught, an e to the 2I omega naught term. But then you also get a mixed product with 4 omega naught. Then you get a mixed product from with a complex conjugate. So you get an A with with 0 frequency, this and its complex conjugate. And then you get this absolute value, this squared gives 6. So the point is you go all the way from -6 to +6 in even steps. So the y2 looks like this. It's like a C plus a D e to the 2I omega naught t plus an e to the 4I omega naught t plus an f e to the 6I omega naught t plus cc. Just to make sure this f has nothing to do with this f. I just wanted to stick with the alphabetic order. And so this is a curly f, where this is a straight f. Okay, and so you plug this in. There's no solvability condition that arises because L only is singular with respect to frequency plus and minus 1, and these are all not 1. And so you can calculate what these guys are. I'm not going to write it out. This is, again, you can find that in the notes. But let's look at what happens at order epsilon cubed. So there we have then d by dt squared of y3 plus omega naught squared y3 is equal to, and now we get terms. What do we get? We get something from the damping. We get something from this second derivative together with the slow time. And then we get something from the quadratic term. Okay, so that means we get from the damping, we get minus beta dy1 by dt. Beta carries epsilon squared, y1 carries epsilon, we're doing epsilon cubed. Then we get 2 times the mixed derivative with respect to fast and slow. So it should be partials. Well, let me make it more beautiful. Mixed derivative t dt y1. And we get minus 2 alpha y1 y2. Okay. And so now, of course, we have to look out for a solvability condition. This guy will have a frequency of omega naught. Okay, so that will contribute to the solvability condition, as will this guy. And here we have to look what happens when we multiply y1 with y2. And so there we also get a whole bunch of different solvability condition contributions. So y1, y2 has terms. Let's see, what do we get? For instance, A times C will have the right frequency, A times C. Then B times D star would have also the same frequency, E times D star. And what else would be there? We could have A star and D. Okay, we have A star and D. And what else is there? We have B star and E. Okay, so B star and E. So we have, I mean, these contributions, they all have e to the I omega naught t. Okay, so you plug everything in, and sure enough, you get the equation as you expected. You get the equation d by dt of A is equal to mu plus mu2 f absolute value squared A minus gamma A absolute value squared A plus delta f A star squared e to the 3I omega t. And the coefficients, I'm not going to write them down, but these coefficients are just some expressions in terms of alpha and omega naught and beta. Okay, so this equation is essentially what we expected, right? I mean, that's what we predicted from the symmetry argument. We said there should be a term fa star squared and the usual nonlinear term. We have this e to the 3 omega naught omega t because we allowed the f to be a slowly varying function, which is not part of that discussion we had here. So that's okay. It's just a little bit annoying because one doesn't really like non-constant coefficient equations. So, but you can get rid of it if you can absorb it into A if you simply shift A, make a phase shift. So if you say A is equal to some curly A times e to the I omega t, then you see that this term is minus 2 omega, e to the minus 2 omega t, but there's overall an e to the I omega t. So together, this will also be an e to the I omega t. And so the overall e to the I omega t will cancel when you've gotten rid of those time-dependent coefficients. So you have d curly A dt is equal to mu plus mu2 f absolute value squared. A minus gamma A absolute value squared A plus delta f A star squared. I have to be careful. when you make that change, the time derivative, of course, produces something from product rule. And so that shows up actually in here. So I think I want to do it this way. Let me call that mu hat. And then actually this mu is equal to mu hat minus I capital omega. And so we see that, again, the imaginary part of this coefficient captures the detuning between the frequency, between the forcing and the oscillator. Note, I mean, this is minor, just, but you know, we factored out a 3 here to make life easier. So it's not the detuning, it's actually 3 times the detuning. Yeah, it's not, that's what it is. It's just, that's fine. Okay, so now we have a relatively, well, complicated is maybe not exaggerate, but it's an equation where it's not obvious what the solutions are, and we have to analyze it. And that's also somewhat of an algebra thing, and I'll do that in the next step. But at this point, we just appreciate that we had an oscillator with a quadratic nonlinearity, which was forced non-parametrically, as in with an inhomogeneous term, and it generated an amplitude equation with parametric forcing and a cubic nonlinearity. And okay, let's maybe just make sure why that is. I mean, we cannot, how could we have in our amplitude equation, how could we have a non-parametric forcing? Well, all the terms in the amplitude equation have to correspond to the same frequency, the same Fourier mode. So that Fourier mode is the basic frequency of the Hopf oscillator, right? Because we have always the dA by dt and also the linear term A. So that means the forcing, if you want to have a non-parametric forcing, the forcing has to be at the frequency of the Hopf oscillator. Because this F is not at that frequency. And so therefore, for the forcing to even show up in the equation, that forcing frequency, which is 3 omega naught, has to be, so to speak, compensated with an A, which is, in this case, we start with 3 omega naught, A star squared subtracts 2 omega naught, and that gives the omega naught. So that's why you don't get a non-parametric forcing, even though you start with that. And it's because the frequency ratio is what it is. We only get non-parametric forcing for one-to-one resonance. Okay. Yeah, so let's, in the next step, let's analyze this equation.